I've taught this lesson, it's got to be 30 or 35 times, and I still sort of get chills as I go to teach it, because this is a fairly easy lesson and it sets up calculus. I'm telling you, all through this semester, teachers do it all the time. They say, oh, this is the most important lesson. This is so important. Every other time between now and calculus, I'll be lying when I say this is so important. This afternoon lesson is so important. Now, don't get all nervous. Not like it's so difficult. It's actually not. It's got a very specific procedure, but it's so vital to everything we do. Reminds me of the grade 9 lesson about slope. You're going to find out that lesson was the most important lesson in grade 9. But it wasn't that hard, really. y2 minus y1 over x2 minus x1. It wasn't the hardest thing you saw ever. Okay, so average rate of change. Right back to displacement time graphs, because the physics examples are the simplest ones to set up. And we won't go too crazy with physics. We'll just sort of deal with these displacement time graphs. Consider the following displacement time graph of Paul's run. This might have been stolen right from grade 9. This is the kind of thing we do and say, can you analyze what's happening with Paul's run here? And so what can we say about the velocity in these three different sections of motion? Well, I'm going to write an extra word there. We would have just said slope probably in grade 9. We would have immediately gone to slope. And that's what I was saying with my poster at the back of the room. Slope is the same as the rate. It's the same as the speed. And I don't think you have to do anything here. I think all these notes are here. You don't have to copy anything. You just have to listen. Earlier in this course and in previous courses, we would have said that Paul moved quickly, or he ran away, or some other qualitative comment. That is, between 0 and 4, we would have looked at this and said, oh, he's moving away. The slope is very large, and so he's running, and his displacement's getting bigger. We would have said distance in grade 9 to not confuse the issue, but his displacement's getting bigger all the time, very quickly, so he's running away for those first 4 seconds. And that might have been the end of what we would have said about it, a qualitative analysis. Now, but the question is, was it really quick? Just because the slope looked bigger than other slopes, was it really fast? How do we know? We don't really know what fast is. And those kind of qualitative words, we're going to try and get rid of those and not go, it's not our place to comment on how fast he was going. We want the number, okay? So where are the numbers? From here on in, we'll answer these questions quantitatively. And what quantitatively means, if you haven't seen that word in other courses in science and so on, quantitatively means give me a number to talk about, okay? And how do we do that? What is the velocity for the first part of the journey? And here's how you calculate velocity. Velocity is the slope. Now, this is where I'm going to really relate the two. And yesterday I didn't really worry too much about y2 minus y1 over x2 minus x1. And I'm not going to here either. I'm just going to head towards it. If I go back to this part of the graph and say, okay, if I want to know his velocity, I want to know how far did he go? He went 8 meters. How long did it take him? It took him 4 seconds. So I can find his velocity. Take his displacement and divide by the time, and we find out he's going 2 meters per second. I'm exaggerating when I say you didn't do that in grade 9. You sometimes did calculate those. A few of the questions in grade 9, you would do that. So if this seems familiar, yeah, pretty much. But this is just slope. That's all that's going on here. Delta y over delta x, rise over run. Slope is the velocity, but in another context here. That, however, is not the important point of this lesson. That's like a review of previous stuff or brushing the rust off on it. Or if you didn't do that at all in previous courses for some reason, it's just me explaining all that. We need some definitions to be able to really get to the bottom of what this lesson is all about. I want to talk about average velocity, and I want to talk about instantaneous velocity. And I'm going to go through the notes in a minute, but I just want you to think about driving, and you can picture me driving my van around this weekend as I take these kids and everybody everywhere they want to go this weekend. Instantaneous velocity, I'm going to jump ahead to instantaneous velocity, is the velocity you're going right now. So for instance, if you called me on my new cell phone that I got hooked up to my van finally, and you called me this weekend and say, Mr. Todd, how fast are you driving right now? I'd look down and I'd see the little speedometer thing and I'd go, oh, I'm going 80 kilometers an hour. That tells you how fast I'm going right now, instantaneously, right at this instant. And the speedometer measures that. But it doesn't measure average velocity, because during my weekend, I'll drive 80 for a while, then I'll drive 20 for a while, then I'll stop for a while and wait for people to do their shopping, and then we'll go in and we'll go to Eastside Mario's and have our lunch, and we'll kill some time there. And meanwhile, now my average velocity for the weekend is not 80. It keeps dropping. To calculate average velocity, oh my, there's a lot of work involved. I need to add up all the distance I traveled, keep track of all the time I traveled, and then divide. Average velocity is over some giant time period like that. So maybe that's the most important thing to say. Average velocity will be between two different times. Instantaneous velocity will be right now. What's going on right now? Okay? So, and that's what I say in the notes here. Think about a car. The speedometer gives you a constant reading of your instantaneous velocity. If you haven't seen these words before, this thing here is called a speedometer. It measures your speed. Yeah? So that tells you your instantaneous velocity. The only time this thing gets messed up, I don't know if you've ever seen this before, if your tires spin, like if you're in the driveway, like on the snow or ice at the end of the driveway, and you hit the gas and your tires spin, this thing goes woo, woo, and you're not actually moving, right? Because it only measures how fast the tires are spinning. So that's the only thing that can mess it up. Let's ignore that for a second and say this speedometer always tells us what our instantaneous speed is. So the instantaneous from the speedometer here that I see on the screen here is about 130 kilometers an hour. To calculate the average velocity, we would use the odometer reading. Okay, just imagine for a second that I got a brand new car at the start of the weekend. And I was driving around, and over the weekend, I drove 200 kilometers. You go, okay, that's a good start to average velocity. I know you went 200 kilometers. Now we need to know how much time you were using to drive around. Then you could figure out average velocity. Not easy to do, right? Average velocity is a little more difficult to calculate because you need the whole distance and the whole time. Fine, which type of velocity is 2 meters per second in Paul's run? Was he going 2 meters per second over the whole time period, or was he going 2 meters per second the whole time? And the answer is he was doing both. See, when it's constant velocity, we don't need two separate words. That's why we just made linear functions in grade 9. We didn't need to separate these two things. That is, if I get in my car tonight and drive 80 kilometers an hour from here to Florida and don't even stop and just keep going, impossible to do, really. But let's just imagine I did 80 kilometers an hour the whole way, and you said, Mr. Tao, what's your instantaneous velocity? 80 kilometers an hour. What's your average velocity? 80 kilometers an hour, because I've been going the same speed all the way through. So if you're going constant speed, your instantaneous velocity is your average velocity. That almost never really happens, except in crazy little grade 9 examples like this. Yeah? So this says calculate the velocities of the other two parts of Paul's run. Again, this is just reviewing old stuff to set up for later things. Well, I hope we're at the point. If not, it's my job in the next few minutes to get you to the point where you can just look at that and go, I don't need to do any calculations. I know what Paul's velocity was in this section of his run. How fast was Paul going during that time? 0, nothing, yeah? M equals 0 or V equals 0. I don't know which one you'll write there. It depends on what your brain's thinking about right there. You might go, oh, velocity 0. You might go, oh, slope 0, velocity 0. So that's not supposed to be particularly hard. One more time through this whole slope thing if you're still brushing the rust off of all that. In this section here, to get the slope, and I'm being a little more specific now, I'm writing down M equals rise over run. He went 8 meters, and it took him only 2 seconds. So he went 4 meters per second. And I, on purpose, have made a little mistake here because I really want to draw your attention to it all the time. And maybe I'm already setting up for next test where you're going to write at the top, watch positive and negative. You know, like instead of, what was it last chapter? Common factor. Don't forget to common factor. This time, don't forget to look for positive and negative because this was, oops, not there. There. This was a negative rise, if you want. His displacement was getting smaller, so he gets a negative velocity in that particular section. All that means is he was heading back to where he started from some point of view. Yes? Any questions about finding slope with nice little straight line sections? You good? All right. More time here? Needs more time. That's not what we really got to worry about. We now, in this course, have to get where we can handle changing velocity. Yes, not just linear functions, and analyze that. find the average velocity for the first 5 seconds. And I believe this is all in your notes. You don't have to do anything here. First round, if you just flip to the next one, I think it's in there. Am I right? It's there on my screen. Let me just look in yours. Consider this new situation. Oh, it's all there. So you can just follow along here. That was my intention. New situation. You can imagine something being thrown into the air and coming back down, something like that, but something that doesn't have constant velocity anymore. Find the average velocity over the first 5 seconds. Well, I'm going to do some drawings on here, but it's all on your notes there. So I'm going to say, well, what I want then is I want to find what's the average velocity between time 0 and time 5. And what's interesting about average velocity that actually makes it easier to deal with an instantaneous velocity is you don't really care what happened here. You're like, when that odometer said 200, you're like, I don't care what you did. I don't care where you went or how you did it. Fast, slow, backwards, forwards, none of that matters to me. All I care about is, where did you end up? How much total displacement did you come up with? And so what we do is we draw this line here. And it's in your notes, but if you want to draw it on the other diagram, just so you really get a feel for it, we draw this line here to connect the 2 dots, where you started and where you finished. And all we got to do is find the slope of that line. So we've taken a really complicated, curvy situation and really simplified it by drawing a line from the beginning to the end. And for average velocity, that's all we have to do. I've probably already given you enough to do all the homework for this section. Yeah? Average velocity, get the beginning, get the end, find the slope. That's all. So in this section here, now the rise is 14 meters. The run was 5 seconds. M equals 14 over 5. And I think on the next page, we're going to see all that stuff is already written down for you. But if it makes you feel better to write it all down because you like practicing these things, that's the whole game right there. Beginning to the end. By the way, it's handy to have a name for this line that connects up 2 points on the curve like this. This line is called a secant. Also going to be the name of my boat when I retire. The Secant. Unfortunately, I've been making that joke for many years, and I still love it so much. There's a picture up here of me and my boat. Someone drew. It's at least 5 years old, this picture, and it's the Secant boat, and I'm doing a stupid Rubik's Cube there. So this is what they remember about me. My Secant joke and a giant Rubik's Cube. Okay, the rest of the lesson is just me doing more of these. So if you're like, oh, I sort of get it, you're really going to get it. Now I'm just going to bore you for 20 minutes while I do more and more and more of these in different setups and different situations. Okay? I think that's all there. Yes? Notice here I did y2 minus y1 over x2 minus x1. I don't think very many people would use y2 minus y1 over x2 minus x1 for this very simple situation. But I'm just trying to throw it in there and set it up that as soon as things get complicated, we got this thing, and if you had my class in grade 9, I used to write m equals y2. We'll see if anybody who took my class remembers this. I get all excited, and I'm like, this is the best equation of the year. And I draw it with a big heart on it, and I say, hey, this is, beautiful. You got to love this thing. Draw a heart around it every single time. It's true, and it's not that complicated. You just subtract the y values, subtract the x values. I'm going to use it like crazy over the next few minutes. A couple of notes. The drawing of the secant line may not seem necessary. I drew a line from the beginning point to the end point. You may think, oh, that's overkill. I know where the 2 points are. I can just subtract them. You may not think that's necessary, but it's an important understanding of all this, and I'm building towards a bigger idea in the next lesson this afternoon and going into calculus. We're really building towards a really gigantic idea. So drawing that secant line helps you build that thinking towards that idea. So trust me on that. The secant line is a good thing to do. All the steps in the calculation may seem like overkill, but they will help as the situation gets more complicated. I'm referring specifically to this step here, this y2 minus y1 over x2 minus x1 move. Overkill for this example for sure, but as things get a little more heated here, you'll see it's a handy thing to have. You've got a table on the next page, am I right? I'm using this to fill out the table. That is, I'm going to do section 1, then section 2, section 3, section 4. I've got it all on separate slides, which you only got one table to do. We're going to just do this calculation for different time values and just see if it gets more complicated as we go. Maybe you're not going to think it's more complicated. Maybe you'll be bored by this time I do the second one, and that would be great news. You're like, I totally get it. Okay, it says calculate the average velocity in these intervals here. It says calculate the average velocity between 0 and 1 second. So I want to know between 0 seconds, I'm going to put a nice big dot there, and between 1 second, I'm going to find that spot on the graph. And again, I don't really care how the person got there for average velocity. I just want to know how much was their displacement and how much time passed. So I just look here and I go, okay. The delta D, how much did the displacement change? You can see it, but follow along with me. It went from 0 to 5, so to find out how far I went, I just do 5 minus 0. You're like, I don't need to do 5 minus 0. I know, it's 5. Stop being so silly. I'm setting up for something. I'm on my way to something. This is how you would find out how much did the displacement has changed by going 5 minus 0. To do the delta T, you'd go, okay, started at time 0, went up to time 1, 1 minus 0. And if you think I'm nuts, that's fine. I'm on my way to making the hard example easy by doing it this way. If you're actually doing this on a test with these two easy ones, you just go, it's 5 over 1, I'm done, yeah? So then to find the average velocity, you just take the delta D and divide by the delta T, and I get 5 meters per second. Now I'm going to do that 5 more times. And hopefully, no matter where you are on the understanding level of how to do that, as I do each example, you'll just move up the scale. And then at the end, I'll go, okay, are we good or no? Because if you're good with these, you'll be pretty good for the last 2 examples and the homework here, setting up nicely for the afternoon lesson. Any questions there, though? Let's do it all again, right from the top. Your diagram's going to get a giant mess. If you're trying to follow along and do the diagram with me every time, you're going to have trouble on the previous page fitting that all in, and that's why I'm trying to do it up here with separate diagrams. Next, they say from 0 to 2 seconds. So I put a dot at 0. I put a dot at time 2. I find it up here. It goes up to 9. And I draw that secant line connecting the 2. You really can't see it because it really just hugs the curve there. See if I can get it in a color that maybe you can see a little better. Hook up the secant line, and all I'm doing is finding the slope of that secant line to find the average rate of change. I don't care how they got there. I don't care how curvy it is or whatever. I only care, where did you start? Where did you end up? So here, if I want to know the delta D this time, I'd go 9 minus 0. On the next one, I'm going to ask somebody to tell me what I would do with the 2 numbers to get it. But I'll do it one more time. 9 minus 0. You might think that's overkill, and you'd be right. No one writes 9 minus 0. They just write 9, yeah? Then delta T, 2 minus 0, so 2 seconds have passed. And then to get the average velocity, take the change in displacement, divide it by the change in time. This person's going 4.5 meters per second. If you're totally bored going, isn't this the exact same thing you were doing at the start with Paul's run, just delta D over delta T? You're absolutely right. I'm doing the same thing every single time, just finding the slopes. If you're like, I've lost you a little bit, I'm going to slow the next one down, because the next one's the first one that's actually sort of interesting, and I'll really slow it down. But, any questions on that one? Okay, then, time 1 to time 5. Now look what happens here. Time 1 is right there. Time 5 is right there. Slightly different look at this. So now these steps matter a little more. After you get your 2 times right there, then draw this secant, it's called. And you don't care how they got there. You only care about where did you start, where did you end up. So now I want to find the slope of that secant by doing rise over run. Now, to find the delta D, what would you do? It starts at displacement 5 and goes up to displacement 14. What would you do to get the delta D, how much it's changed? 14 minus 5. And maybe for the first time in high school you go, oh, I totally get why the slope formula is y2 minus y1 now. I'm just finding out how far this thing went, 14 minus 5. And I'm sure there's somebody out there that's going, I don't need to do 14 minus 5. I can see it's 9. I don't know why you're making a big deal with that. I'm setting up for when it's not 14 and 5, it's 12.72 and negative 32.1. I'm setting up for complicated situations. There's nothing complicated that you have to do. You just have to subtract the 2 values. So I get 9 here. Now, how about the times? I started at time 1. I ended at time 5. What would you do with those 2 values? You can probably do it in your head. But what's the mathematical operation I have to do to find out how far it is between 1 and 5? 5 minus 1. It's the difference. How different are they? Finally, maybe that word makes sense after all these years. In grade 2, they say, find the difference. You're like, why is it called the difference? Because you're finding out how different they are. 5 minus 1 is 4. And then to get the average velocity, I take the displacement, divide it by the time, and I get 2.25. Now, if you're starting to think, well, wouldn't it be easier to actually just write the coordinates on here? 1, 5, and 5, 14, and actually do y2 minus y1 over x2 minus x1? I 100% agree with you. That is a great way to handle these things, is to write the coordinates. And on all the next examples, I'll write the coordinates down, and you can just use this beauty. And we're just going to use this like crazy, over the next few lessons. I just about said few days, but that's regular school. For us, few days is few hours, yeah? Okay. 2 more times on this table. I'm going to slow it down again. If you want to find the average rate of change between 2 and 6, put a dot at 2, put a dot at times 6, and draw that secant line to say this is where we started, this is where we ended up. Because I don't care how you got there. I only care about where did you end up. One more step in the procedure now is to actually just write the coordinates of these points on there. Maybe that's a little easier to follow what's happening. Is there's the first coordinate, 2, 9, and here's the other coordinate, 6, okay, now let me set up the rest of the lesson. Graphs stink. They suck. It's terrible. You're always stuck with estimating things. You know, it's good for visualizing. It's good to see what's going on. But if you want specific values, if you want accuracy, you need the equation. Yeah, the equation really gives you perfect numbers. And that's where we're headed with all this. This is just getting the idea. We want to do this with equations so we get perfect numbers. So I'm stuck with estimating here. To me, it looks like 13.3. You look on the completed notes online, maybe I chose 13.5. I'm not going to bust you on. I'm not going to look and go, oh, no, that's 13.278. You know, no. When you're given the graph, you just best estimate. Close answers are as good as we can probably do. Okay, someone tell me then, how do we get the delta D? I really want you to be right with me here. What would you do with the values you see on here to find the delta D, to find out how much the displacement's changed? 13.3 minus 9. You're just subtracting to see how much. Yeah? You see how it's a little more complicated now than just going, oh, I can see how much it is. 13.3 minus 9, I get 4.3. That's just y2 minus y1. That's all I'm doing there. Then x2 minus x1 is 6 minus 2. And then to get the average velocity, I'm finding the slope, take the delta D, divide it by the delta T, and here I get 1.075, I think, when I punch that in my calculator. 4.3 divided by 4, 1.075. Hello? I didn't hear what he said. Yes, Sarah Wilson is here. Can you come to the library for a guidance appointment? Certainly. My ears don't work as good as they used to. You got that to look forward to when you get older too. Spend your whole life going, what? What did you say? In grade 9, we always kept this as a fraction because we were going to graph them. Here, we'll most often go to the decimal because we want to know the number. Yeah, so slight thing. You got that pounded into your brain like, no, leave it as a fraction. I was told to leave it as a fraction. Yeah, I know. The rules are changing as we go along here. Yeah. One more time, 2 to 9. Time 2, right there, to time 9, right there. In this one, now you'll finally see the big advantage of just writing the coordinates. The coordinates will set you free, okay? What I mean by that is a couple of times on purpose I've made a mistake with the negatives and had to go back and go, oh yeah, it's negative. And you're like, oh, maybe I'm going to forget that it's negative. Watch what happens here if I just write down the coordinates. 2, 9, and the coordinates here are 9, 5. See, make sure I got those right, 9, 5, 2, 9. And I'm going to go y2 minus y1 over x2 minus x1. y2 minus y1, 5 minus 9. The negative pops out of there naturally. The formula's got it. He's like, the formula's looking at you, I got it covered. Don't worry, I got the negatives. You don't even worry your pretty little head about it. I'll take care of the negatives. Yeah? The formula does that for you. Now, x2 minus x1, 9 minus 2. And so I get negative 4/7, which is negative 0.6. I'm just rounding to one decimal place. One decimal place is fine for what we're doing. Maybe on other courses at different times you want 2 decimal places. You can make those own decisions as you go. I'll always be pretty specific on tests and so on. I'll say, oh, let's do 2 decimal places there, or let's do this many decimal places. This afternoon I'll be really specific about decimal places. Questions so far? Well, now I'm going to do it with the table values and with an equation. And some people will find that actually what I'm going to do next is easier than all this. Some people find it more difficult. You got to let me know as we go along. More time here? So far we have dealt with the familiar word for rate of change, velocity. Physics has a fancy word for rate of change, velocity. Other fields sometimes do, but sometimes they don't. In chemistry, they're a little lazy. They just say average rate of change of temperature. They don't have a fancy word for it. In business, they have a fancy word. They go marginal revenue. That's the rate of change of revenue. So it depends on the field you go into, whether there's a fancy word or not. Most often, the best we can say is average rate of change. So in this case, we were doing velocity was the average rate of change of displacement. So let's go to a situation that you might see in, say, a chemistry class or a biology class, something like that. Consider the following chart, which gives the temperature for certain times and answer the given question. So some readings have been taken. At time 0 seconds, this was the temperature. Time 5, this is the temperature. Something was being heated up, and the temperature was recorded at all these different times. Very accurately, by the way, 94.550 degrees, like they have perfect temperature readings here. He says, the question is, what is the average rate of change in temperature for the first 30 seconds? So they're giving you the time 2 times. It doesn't look like they're giving you 2 times, but they are. They're giving you time 0 up to time 30. Can you see how this is much easier than the graph? You don't have to draw the dots on it and find the points and everything like that. You've got the points. Let me highlight them for this question in yellow. There's the 2 points we're talking about. Average rate of change between those 2 points. Now, in setting up for later things, I'm going to write some weird symbols here, but it's really all I'm going to do. The only thing I'm going to do is y2 minus y1 over x2 minus x1. That's what I'm going to do. But what I'm going to write is I'm going to say average rate of change. And as you're writing that and your wrist is hurting, as you're writing all of those words to calculate something, don't worry, I got a shortcut coming, okay? For now, we'll write average rate of change because we're just learning about it, but I've got a shortcut coming. Here it is. In math, we call this AROC, average rate of change. So you've got a nice shortcut there when you go to do your homework and so on. Yeah? And even on their test, I'm not going to be like, oh, no shortcuts in the test. No. AROC is good. We'll say AROC and IROC all the time. I'll keep trying to use the words to remind myself that I'm teaching it, not talking about it, so you know what I'm talking about. But anyways, average rate of change equals delta T over delta T. I'm trying to teach a little science here in the meantime. Capital T is almost always temperature. It's like reserved for that. Temperatures is capital T. Little t is almost always time. It's like reserved for that. I'm not saying they can't be used for other things, but scientists pretty much use those that way. And so then what I'm going to say is, to find the change in temperature, I got to find the temperature at time 30 and subtract the temperature at time 0 over 30 minus 0. And if you're like, okay, I was really getting what you were saying here, and now you're writing all these crazy symbols and messing me up. No, I'm up to something. I got a big plan that these symbols will bail us out. These symbols will be our power, our ability to handle big questions. Okay? Now when I fill these in, maybe you'll go, oh, I see what you're saying, but I'll do it slowly. The y2 minus y1 is take the temperature at time 30, which is the 94.496. And I've put this short form right in my way here. Let's see if I can. Oh, it's not going to let me grab it. Okay. Well, I'll use the short form in a second. Okay, go. That was the temperature at time 30. It's the y2 if you want, but it's not y's here. It's t's. You see? Like, the y2 minus y1 in grade 9 was just like, well, we don't know what you're going to be talking about. We don't know if it's going to be temperature or height or money or profit, so we'll just call it y, okay? And so now you actually have them. So this is y2, in this case, y30, minus y0, well, temperature at time 0, 86.756, all over 30 minus 0. And so in the numerator there, by the way, in the interest of keeping your notes small, I'm totally breaking a math rule of going equals, equals, equals across the line here. We're really not supposed to do that. We're supposed to go down the page. And from what I've seen of your tests, you know that. But hey, for this example, it just was in tight space here. So I'm just going to subtract the tops there. 94.496, subtract the 86.756. You see, and remember the first example was like 0 to 5. You're like, why are you going 5 minus 0? I can see it's 5. Not quite so easy now. Yeah? And so the y2 minus y1 move is important. Make sure I type that in right. I get 7.74 over 30. And so what I get here is 0.258. Oh, we got to start getting better at units. Yeah? Units all the way through, we sort of ignored them in math. Now we've got to talk about this. What's changing? The degrees Fahrenheit is changing. How's it changing? It's changing over seconds. So this is 0.258 degrees Fahrenheit per second. I don't like how big I wrote that little degree symbol, so I'm going to do a little better here. Degrees Fahrenheit per second. Now I got to tell you, your science teachers are really going to get on about units, and they should. And I will as well. I'll put little red marks in your test when you don't do units, and I'll sort of do the, I don't know, we call it at my house the pee-pee dance. Have you ever seen a little kid and their whole body objects to what you just said? Yeah? You say to a little kid, okay, I want you to go brush your teeth now. And they're like, and their whole body just freaks out. That'll be me marking your test. If you don't have units on there, I'll be like, at the same time, there's so much math going on. I just don't have it in me to take a half mark off in the middle of all that. You know, because I'm like, oh, you got all the math right. I'm so happy. Things are going so well. You're going to calculus. You're going to university. Everything's going to be great. Forgot the units. Yeah? So I will mention it. I'm not saying I won't ever take marks off for units, but really try to get the units. You know, okay? Question? Okay. Next, average rate of temperature from 15 to 40. Exact same question, just two different time periods now. So it says, I'm going to highlight these ones in green. 15, that's not green. 15 to 40. So I've just got a different two set of points. But I'm going to go through the whole thing again on the off chance you're having trouble with it. So here comes the short form. Average rate of change equals, and please write down everything I write here. It's going to help us as we move forward to be able to see all the little things I'm putting into this. To find the average rate of change, we want the total change in temperature over the total change in time. That's what we're up to. That's what those little delta symbols mean. Delta just means, up here, a short form in math and science that means change. How much have you changed? So to find the change in temperature, does anyone want to take a shot at it? What would you write in here using our function notation instead of y2 minus y1, x2 minus x1? Not that I have a problem with that. What are the two times we got to deal with here? 40 and 15. So the top is going to be temperature at 40 minus temperature at 15 over 40 minus 15. And I just plug them in. 94.784 subtract 92.678 over 40 minus 15. Incidentally, this is the chapter where you really want a great calculator. Yeah? And so make sure you can type these things in and get these answers efficiently. You're like, I can't give up my calculator. I love it so much. Well, you can carry it around with you if you want. Just don't use it anymore. I get 0.08424 degrees Fahrenheit per second. You're like, how many decimal places? Don't get too freaked out about decimal places just yet. I'm going to talk lots about decimal places as we go along here. So for now, I just kept them all. Any questions there? I've got 9 minutes for the last example. If I've set it up just right, the last example will be the easiest one. If I've set it up just right. Pressure's on me. You tell me how I did. One more question with an equation instead. They want the average rate of change in height between 2 and 3 seconds. So I want average rate of change. So I need delta H over delta T this time. Change in height divided by change in time. Is this example there? See some people flipping around, but okay, it's good. So what I want is, what's the height at time 3 minus the height at time 2 over 3 minus 2? And if you've been keeping up with the homework, all of a sudden this might seem familiar, like, oh, I see why they've been asking the questions they have been asking. They were setting us up for chapter 2 the whole time. This kind of question drove some people nuts about, what do I plug in and where? And that's what they were setting up for, was exactly here. So I do them separate. Like, I go off and I go, oh, I need H at 3 and H at 2. So I go over here and I go, oh, find H at 3. And I sub that in. And then find H at 2, and I just go over here and sub that in. That's the way I like to do them, is when I need things from a function, I go off to the separate like this and I plug them in. Let's just make sure I plug those in right. Yeah, I think I did. And then again, you should, when I finish this lesson, the first thing you should do is get your calculator out and punch this in and make sure you get the answer I do, so that you know how to use your calculator. And if you have trouble with your calculator, just call me over. I've seen all the calculators, so I know I can help you out with it. 3 plus 1 squared plus 108. I just typed that all in. I didn't do bed mass grade 9, show all the steps. No. I have this weapon, the calculator. We got more important things to do than show every little step in these. So your calculator will handle this. Punch it in and get the answer. And then this one, negative 4.9 times 2 plus 1 bracket squared plus 108. If you have trouble punching those in, call me over. Spend the weekend getting to know your calculator, like quiet dinner and a movie. Just you and your calculator. Getting to know all the different, no more borrowing calculators. Like, you have to know yours really well. So that this goes quickly. That's the whole goal here. Now I'm ready to go back to here. I found the height at time 3. It was 29.6. I found the height at time 2. It was 63.9. I've done that little simplification on the bottom. And look at this. It's my favorite moment in the whole lesson. 29.6 subtract 63.9, negative 34.3. And what's nice about that is the formula took care of it for you. It's like, don't worry about negatives anymore. I got you covered. You just plug it in. The negatives will take care of themselves. And that's what's nice about these formulas. You don't have the graph to look at to decide if it's positive or negative, or even a table of values, but you got the equation. You also have exact numbers, which the table can't give you, or sorry, which the graph can't give you. Okay, 6 minutes to go, and I forgot one thing. Who's got it? The one thing I forgot. The units. Yeah? Please really try. It's really important for your science career, if you're going off into sciences, that you get the units all the time. And here, did they give me the units? Oh, they didn't give me the units. This was supposed to be in meters. I'll be really careful about that on tests and so on. And the homework's really careful about that, about mentioning the units in the question. So then you go back to the units and you go, okay, meters per second there. And technically, I won't, again, proper math communication, you should really, on the last line, write a rock again. And maybe you should even have a statement here. Therefore, the average rate of change was negative 34.3 meters per second. Last question for you. What does the negative mean in this question? A rock was thrown off a cliff, and between 2 and 3 it had negative average velocity. What was the rock doing over that time period? Yeah, it's going downwards. So pretty easy interpretation here, and that's why we use physics sometimes in this, is you don't have to understand much about physics to be able to go up, down, whereas if we were using chemistry or biology all the time, it might be a little more difficult. Any questions there? Oh, we hit the time. We hit the time.